Hi everyone, my name is Bentley, and today we'll be giving a structure tour of Peters Parking Deck. Peters Parking Deck is located on Fowler Street Northwest in the east part of Georgia Tech's campus and also located centrally. Now the current use of Peters Deck. Currently this structure acts as a parking deck for the first and second levels, and the third level above me acts as an entertainment and recreational use that hosts tailgates and also has basketball and tennis courts. Previously, Peters Deck was just an open green space and was a park before this was built. Now some history about this structure. Before this deck was built, this land that we are on now was donated by the Peters family to Georgia Tech for use as a green space or park. But according to our fathers who came to Georgia Tech in 1987, this structure had concrete deterioration even at that time, so we really don't know when it was built. Now the lack of information about this structure could be due to the controversial fact that Georgia Tech was donated this land by the Peters family for the intended use of a park and green space, but they decided to build a parking deck on it instead. The technical significance of this structure is that it provides parking to students and faculty that live and commute to campus. One note is that the lower deck often has flooding during heavy rainfalls due to the fact that it is below the grade of the surrounding roads. Now we will look at the materials that make up this structure. The materials of Peters Parking Deck is mainly concrete, and the materials that we see here today are the original materials, although we can start to see some concrete deterioration. As well as the concrete that we see here, there's also facades that aren't part of the actual structural members. These facades are acting mainly on the top level and subsequent levels to provide some sort of safety and wall to prevent cars and individuals from falling off this deck. Many of the components in this structure were from precast facilities, such as the double T's that support the cast-in-place floor slabs, but cast-in-place can also be seen on the columns and girders of this structure. Concrete was chosen mainly for this structure because of its high compressive strength for the columns, yet the reinforced concrete is also useful in members that experience tensional loads such as the girders and double T slabs.
Hi, I'm Will Noble, and I'll be picking up the tour of Peters Parking Deck here with the construction methods used. As Will already said, there was not much information available about the history and construction of this parking deck. However, based on historical data, we were able to come up with a range that it was probably built in around 1 year, just because of the sophistication and construction materials used. Some problems that could have occurred, as Will's already mentioned, this area is below grade for this area, which means flooding could have occurred, as well as just building in Atlanta presents a lot of logistical problems which could have led to delays in construction. Will has already talked about the materials used, which were a lot of precast materials, which incidentally speeds up the construction process and makes the process a lot easier for the workers on the job because there's a set process for the assembly of these materials. The design of this parking deck was conceived by Georgia Tech and an architect who then were able to consult with a structural engineer to come up with the final design, and then a construction engineering firm was hired with several subcontractors who had their own workers to build this parking deck is how it was constructed. We are now standing on top of Peters Parking Deck, which, as you can see behind me, there's a tennis court as well as a basketball court. The design of this deck needed to make sure that the floor slab, which I am standing on, can hold the weight of large amounts of people as well as the weight of the concrete that the floor slab is made up of. This floor slab transfers the weight down to double T beams, which we will see next. We are now on the second floor, directly under where we just were on the tennis courts. The double T behind me, as you can see, is taking the load from the floor slab as talked about. These double T beams are transferring the weight from either side of this floor slab onto girder beams, which then take this girder beam will actually be the focus of some of our analysis later in the video. This girder beam also takes the weight from the double T beams, which are taking weight from the floor slab onto these columns, which transfer the weight all the way down to the ground. We will be using this rectangle of Peters to use for analysis of everything because it's a symmetric structure. We're now on the bottom floor of the structure, next to a column similar to the column we were just standing next to on floor 2. Similarly, this column is taking the weight from the floor above it, as well as all of the weight that's being transferred to it from the second and third floors of the structure. This column is then transferring all of this weight into the ground. Due to the geometry and symmetry of Peters, the load path analysis was relatively straightforward, and we found it to be quite simple because it was the same for each level.
Now, after doing our load path analysis on Peters parking deck, we can do an analysis of one structural member of this deck. We'll be looking at a second level girder and the gravity loads for this girder result to 75 pounds per square foot. This is a result of the self-weight of concrete, which is 150 pounds per cubic foot, and then the estimated 6-inch floor slab above us. These will be the only weights since the third floor above us is a recreational area. As mentioned before, just tennis courts and basketball courts occupy this area, so the loads of individuals and equipment will be minimal.
Using measurements taken by tape measures and also the approximation of the load of the concrete, which is 75 psf, we're able to come up with some formulas to use tributary area to find the loading on this girder behind me. We found it to be approximately 115 kips, which is spread evenly across the girder because there are 3 double T beams which come down and produce 6 point loads on the girder. This can be seen on the free body diagram, which we'll display. This free body diagram shows that there are 6 loads that are symmetric on the beam being supported by 2 reactions on either side, which represent the columns. Because these loadings are symmetric, we're able to also draw a free body diagram that has a distributed load, which we can use for the deformation loads.
For the structural analysis of this member, some estimation was required. Although we found accurate measurements for the dimensions of the girder using a tape measure, the estimates of the thickness of the slab were used based on prior knowledge of deck design. We also assumed that the self-weight of concrete is 150 pounds per cubic foot. This information was found online. Also, we found that the average modulus of elasticity of this girder, being concrete, was found to be 6527 KSI. Now for our structural element, we will estimate the deformation of the beam. Using the Steel Construction Manual formula for maximum deformation at the midpoint, the formula is 5 times the distributed load times the length of the girder to the 4th power over 384 times the elastic modulus times the moment of inertia. Since we're assuming the girder is under a distributed load, which the equation I mentioned earlier demands, we have equated this distributed load from the 3 double T slabs onto the girder to be 0.63 kips per inch. The length of this girder is found to be 324 inches, and the modulus of elasticity was found to be 6,527 KSI. The moment of inertia was calculated to be 2160 inches to the 4th. This was calculated using the moment of inertia equation for a rectangular cross-section of 1/12 times base times height cubed. We measured the girder's cross-sectional area to be 15 inches on the base and 12 inches on the height. Using all these values mentioned before, the deformation was found to be 3.6 inches. And the deformation direction is in the negative y direction or downward direction. This makes sense because the double T slabs are causing a positive internal moment of inertia, creating the smiley face direction of bending. Although this 3.6 inches is very high, this could be due to unknown modulus of elasticity due to the reinforcements that could be in this concrete, information that we do not know.
This concludes our structural analysis of Peters parking deck. This was a really cool project because we were able to analyze one of the most recognizable and most used structures on campus, especially being kind of in the heart of everything here in Georgia Tech. This was also a really cool project because the load paths in parking decks are extremely obvious, which allowed us to apply the information we had used in class to an actual structure here in the field. So it was cool to be able to see this in action.